So we're going to go through chapter 9 and discuss the independent t-test, which you'll notice your textbook calls it two independent samples t-test, but I often just shorten this and call it an independent t-test. So in case you're confused by this. So when we are talking about any type of test that's an independent test, specifically in our case for right now, the independent t-test, this is what is known as a between subjects design, meaning basically that there are different people in each of the groups or in each of the conditions. So we don't have the same people in condition A and condition B. These are completely different people that are independent of one another. So we're looking at the difference between subjects rather than within the same subjects. So one of the terms that you'll be exposed to, and mostly you'll see this within your statistical software, such as PSPP or SPSS, is the term used as factor. Now, factor is basically the same thing as independent variable or quasi-independent variable. Is what it is it's just a term that is used in the statistical software to ask us which independent variable we'll be focusing on, or quasi-independent variable. Instead of distinguishing between a true independent variable or a quasi-independent variable, they've come up with a short term just called factor. And so each factor can have different levels. So for example, if we're looking at gender, there's two levels, male versus female. So that's one independent variable right here, or quasi-independent variable if we really want to be technical about it. So that would be one factor, basically, gender. And then we have personality. Well, that's another factor or another quasi-independent variable. And both of these could be measured on response time. So those would be our dependent variable. So all of these could be measured, but they each have levels. So the gender has two levels, male versus female, and personality has level. Type A personality versus type B personality. Just in these two examples specifically, there could be many more levels. It could be, when we're looking at personality types, it could be A, B, C. It very well could be. So it just depends on what you're presented with as far as the data is concerned. So with the independent measures design, there's some key things to think about. Now, you'll hear the terms independent measures or independent samples, and these terms are generally just terms that are used for a discussion about the research design, basically meaning that there's different participants being observed in each of the conditions, that the participants are not the same participants in the conditions. So they're independent of one another. Now, when we are very specifically talking about an independent samples t-tests, we're talking about two conditions. So think about when you think T, think about two, for two means. Even in a one sample t-test, the T is standing for two because you are looking at the difference between two means, the sample mean and the population mean. With the independent samples t-test, you'll be looking for a difference between the two sample means, which will be inferred about the difference between their corresponding population means. So really that's kind of how to distinguish what is so different about a t-test. So when we're discussing t-tests, there, especially with the independent t-tests, there are what are known as assumptions. Basically, we have to meet this certain criteria, these assumptions. We have to meet these assumptions for our results to be valid. Otherwise, if we don't meet these assumptions, our results are more than likely problematic and would have a problem publishing, would have a problem really being able to truthfully say that there was significant results or a lack of significance. So one of the assumptions is normality. And with normality, there's two different ways that we can assure normality. So you're going to be asked in the future, how do we assure normality in our research results, that we met normality in our data? Well, there's two ways. The first way is you want to look at your research scenario and make sure that each of your samples are greater than 30. So remember, like, well, greater than or equal to, we could say. So we know that at a sample size of 30, we start meeting normality. If we can't assure that, or if our samples are not greater than 30, there's a second way we can assure. The second way is the population is normal. So the samples were taken from a normally distributed population. So this is something that would be stated within the research scenario. So you should be able to say one or the other when it's related to normality. Either your sample size is larger than 30 or larger, or the samples were taken from a normal population distribution. The next is independence. And this can be assured just basically biologically thinking about the research scenario. The scores for the people in group A should be independent of one another. So the people in one condition shouldn't be influencing each other, nor should they be influencing the scores in the other condition, meaning that the people are independent of one another. So let's say if you were testing IQ scores, but you were testing to see if there was a change in IQ scores, you use the same people before and after. Well, how high an IQ score a person has before is definitely going to affect how high their IQ is after, right? Well, if you have people who are different people completely, their scores are going to be independent of each other. So you don't have any people kind of overlapping and influencing each other's scores in any way, shape, or form. So that's at the most basic level, is the outcomes are completely independent of one another. Third is random sampling. So this one, you might have difficulty being able to tell whether you've met this assumption unless you read through that research scenario. Most of the time I'll state, 15 people were randomly assigned to this group and 15 were randomly assigned to the next group. That would assure random sampling. There might be times that you get a hypothesis test or a research scenario where I don't make any statement about random sampling. And if I ask you, were the assumptions met, and I don't say anything about random sampling, then you need to state, I cannot assure that random sampling was used per the research scenario. So those are just things you have to be able to think about. It's just really being able to use the information that you're provided to answer those questions. And the fourth is an extremely important assumption for independent samples t-tests. And this is called homogeneity of variance. And your textbook introduces it as equal variances. I don't like to use the word equal because equal, for many people who think very black and white, equal means exact, right? What we want is homogeneity, which it means a lot of similarity, basically. So what we want is our samples to have variances that are similar, but not terribly different from one another. We don't want to have, two samples where one has a variance of 100, but the other has a variance of 5. That's a huge difference and would be really problematic to ensuring that our results are really valid results. So this is something that we have to mathematically test, or we test it using statistical software. So you'll be learning how that works as we go through the steps. So some new things with the independent samples t-test, first and foremost, is how we set our criteria. It's different than in the one sample t-test because now we have two samples. We have two sample means. So we have to account for the degrees of freedom for both of the samples. So when you see the n of subtext 1 and n of subtext 2, this is basically the sample size for the first group, sample size for the second group, minus 1, and you add those together, which is the same thing as the degrees of freedom for group 1 plus the degrees of freedom for group 2. Another way that it can be done is using capital N minus 2, capital N being the total number of scores in the entire study. So if I had N of 1 equals 6 in the group 1 and N of 2 equals 6 in the second group, well, my N, capital N, in this case would be 12. So my degrees of freedom would be 12 minus 2, which would be 10 for this independent t-test. So you would need to combine those degrees of freedom for the two groups. So capital N in this case doesn't talk about population size. This is talking about the total number of observations in the entire study. So that's where we can start seeing some of our notations being kind of used interchangeably, so you need to be careful. So when you set that criteria, you would find the degrees of freedom and then go into your appendix, the T distribution table, which is C2, using the degrees of freedom and the provided alpha level, determining whether you're using a 1-tailed test or a 2-tailed test, and find the critical value. So we will be going through one together, and so it'll help you kind of navigate this. So before we go through an example problem, let's learn about what the overall test statistic equation, what it looks like, as well as what's going on within the functions of it. So now we're looking at taking the difference between the two sample means. So meaning you're going to have to get a mean for your sample 1 and a mean for your sample 2, and that's going to be in your numerator. And that really is that treatment effect, the difference between the two sample means. And then in the denominator is your estimated standard error. Now, this is something that many students kind of mix up, because this is a long notation, but this entire thing is a notation. It's not an equation. And within that is a couple of equations within equations. So if you remember in the single sample t-test, our estimated standard error notation was S of M. Well, think of this M as we only had one sample mean. So that estimated standard error just was S subtext M. But now we have two sample means, so we have to think about the difference. So S subtext mean 1 minus mean 2. But we're not actually subtracting the mean 1 or minus the mean 2 in that denominator. So be really careful that you understand that that is just a notation. So here's how we get that estimated standard error. We have to get the estimated standard error after we get the pooled variance. So if you'll notice, here's the notation, and here is the entire equation for the estimated standard error. But again, you have things in here that you don't recognize, like this, SP squared. SP squared is your pooled variance, okay? So that's where I said you have equations within equations. Your pooled variance is basically you take the variances of the two individual samples and you pool them, or do like you did a weighted mean. Sorry, let me move that. Like you did a weighted mean in the past. You're going to pull those variances together. So if you recall, the variance equation was sums of squares divided by degrees of freedom, right? Well, now, if you notice, that's very similar. Now we have the total of the two different sums of squares divided by the total of the 2 degrees of freedom. And that's our pooled variance. So that means you're going to have to get a sum of x for each group, a sum of x squared for each group, and the sample size for each group so that you can calculate this out. Now, I have given you another equation that looks different, but it's basically the same thing. So often, like on exams, for time's sake, I'm not expecting you to calculate from a raw data set and calculate out a sums of squares. I often will give you this for each sample, the variance. So is what you would do is take the variance for sample 1 and multiply it by its own degrees of freedom. And that basically gives you this, sums of squares. Then you're going to take your variance for sample 2 and multiply it by its degrees of freedom so you can get your sums of squares for the second group. You add those together and then you divide by the degrees of freedom for group 1, degrees of freedom for group 2. So you just have to be aware of how that equation works in case you're needing to use it. Once you get your answers, you plug them into the standard error equation. Now this is very important when you're plugging things into your calculator, that you're doing them in the right manner. So for example, in this top equation, if I do sums of squares 1 plus sums of squares 2 divided by degrees of freedom 1 plus degrees of freedom 2, if I don't put any parentheses, basically it's going to take the sums of square for group 1 and add it to the fraction of sums of square for group 2 divided by the degrees of freedom for group 1, and then add that total to the degrees of freedom for group 2. We don't want that. So what you need to do is put parentheses around the numerator and then parentheses around the denominator. Okay, so that if you're doing it all in one like that. Now, for the estimated standard error, these pooled variances divided by n, make sure that these are separate fractions. This is not all one fraction. They're two fractions added together. And these are sample sizes, not degrees of freedom. Remember, degrees of freedom is only used in our variance. So that pooled variance uses degrees of freedom. Our estimated standard error never uses degrees of freedom, always uses sample size. So the way that I plug this estimated standard error equation into my calculator is I do, because the pooled variance, we're always going to use equal sample sizes. So in this class, you'll always have the same pooled variance in the numerator of those two little fractions. Let's say my pooled variance is 10, okay? But my sample size is 15. I'm going to put 10 divided by 15 into my calculator times 2, because that'll account for those two fractions. Then I hit equals, and then I take the square root of that amount. So don't forget the square root of that. That's a very, very important concept. So here's an example of an independent samples t-test. So basically a researcher believes a new therapy technique will decrease depression more than traditional cognitive therapy. Basically right there is your alternative hypothesis. You can get rid of this, plug this in as H of 1. A new therapy technique will decrease depression more than traditional cognitive therapy. Your HO would just basically be will not decrease. That's all it would be. We have our independent variable, the new therapy versus traditional cognitive therapy. That's your IV. Depression is your DV, and decrease is your direction. So that's suggesting one tell, right? And it'll be negative, right? Negative t critical value is what it'll be looking at. So in order to study, we randomly sample individuals to participate in either the traditional therapy or the new therapy. Right there, that random sample, that's a key phrase, because if I ask you, did we meet the assumption for random sampling, you can say, yes, we did, because it was stated. So when we're doing setting up our independent t-tests, always note that the group 1 should consist of our treatment group, or the group that we hypothesize to be different. So as you can see, the traditional cognitive therapy is group 2, and the new therapy is group 1, as you can see. So now we're going to go ahead and go through the steps. We have the hypotheses. So the new therapy will not decrease depression more than traditional cognitive therapy. That's our null hypothesis. I am still seeing a lot of you as students mixing these two up. If you are saying the new therapy will decrease and you have an H of O, it's wrong. So make sure H of O means no change. H of 1 means a change. So this one says will decrease. That's the actual prediction. So that's step 1 of our hypothesis testing. It should include our clear distinction of what our independent variable is, what the dependent variable is, and whether there's direction or not. So the next step is to set the criteria, meaning locating the critical region. And for you, when you're hand calculating, that means giving me your critical boundaries or critical value. So we're going to take our 2 degrees of freedom and add them together. If you remember, we had 2 samples, size 5 each. So if we took the degrees of freedom from both, it'd be 4 plus 4. So our degrees of freedom that we're going to use to look up the critical value will be 8. And we'll look in that table C2 and look at alpha 0.01 1-tel. We no longer have to split those, remember, like we did with the z-tests. If you notice, you'll come up with 1.860. This is where you actually have to determine, okay, if I'm looking for direction, is the mean expected to fall on the lower end or the upper end? And since how we're saying the mean should decrease, the depression should decrease, that critical value should be a negative. So be very careful about that. So here is our raw scores. And we're going to go through, and these are all the things that we're going to need, bear with me. All the things that we're going to need to calculate everything for this test. So what I always recommend students do is write things down. So write down your equation for the t-test. So mean 1 minus mean 2 divided by the estimated standard error of the mean difference. Okay? And then there's basic calculations that you're going to need. I always say, write yourself a legend. So calculating each one of those. So 42 plus 37 plus 42 plus 36 plus 34 is 191. So I always write like a little legend down, 191. And then I'm going to divide that by the sample size right away, and I'll get our mean, which is 38.2. Okay. Our sum of x squared for the first group, as you can see, is 42 squared plus 37 squared plus 42 squared plus 36 squared plus 34 squared. So that's 7,349. And then that makes it easy for us to get our sums of squares for that group 1. I just take 7,349 minus, and I do a parenthesis, okay? My sum of x, 191 squared, divided by the sample size of 5, because we're only dealing with the one sample, parenthesis, and I hit enter. And our sums of squares equals 52.8. So then we'll do the same thing for the group 2 and complete these. I always say create a little legend with notations, so that way you can stay organized and plug and chug. Really, ultimately, independent t-test takes much more organization because you're dealing with more numbers. It's very easy to accidentally put the wrong numbers in the wrong places if you don't have them organized and set up with a legend with notations. So really, it's not about are you a great math wizard, is it can you stay organized? That's a really big method for success in statistics. So we'll move on, and you get the gist of going through that process. So as you can see, the sum of x for group 1 was 191, sum of x for group 2 was 204. The means for both of those groups were calculated, 38.2 for group 1, 40.8 for group 2. I can automatically fill those into the numerator of my t-statistic. So that's what I do. I write that statistic down, and then I always put like a little equal sign, and I can start kind of plugging numbers in as I see needed. So now we need to work on the estimated standard error. That's kind of the hard part because there's a lot of equations within equations. So what we're going to need to do is get our sums of square for each group so that we can get our pooled variance. So you're going to need to take your sums of square for group 1 separately and your sums of square for group 2 separately. If you remember, here's our equation for sums of square, the sum of x squared. Then we have the sum of x total squared and divided by n. And n is interchangeable. In this case, think of lowercase n because you're only going to put in how many scores are in that sample. So here's kind of that example that I gave you if we were provided variance. So in this case, let's say you were given this legend from me, and you could see I gave you means, I gave you sample sizes, and I gave you variances. This is the equation you would use if you were provided variances. So ultimately, your equation would be 13.2 times 4 plus 21.7, 7 times 4 divided by 4 plus 4. That would be ultimately your equation. And you would get the same thing as if you calculated from raw scores. It's just makes your life easier. So here is, we did have raw scores though. So you did need to go through and calculate from the beginning. So we had, if you remember, the sum of x totals. So I always put those, as if there were parentheses here and here. Those were just the sum of x's. You would square them, and so that those could go here. And the sum of x squared is each x score squared, 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 and then added, okay, to a total basically. Same thing here. So those would go in this spot to calculate your sums of squares. So here is what we should be getting. A sums of squares for group 1 is 52.8. Sums of square for group 2 is 86.8. It's as simple as that. A clue is if you ever get a negative sums of squares, you know you've done something wrong. And is what you've probably done wrong is mixed up this and this. Like you basically exchanged these. So if you get a negative, that is more than likely what you've done. So once you get your sums of squares or your variances, you can test for homogeneity of variance, that equality of variance. This is necessary. You need to test this. So especially for your lab assignments, you should be testing for homogeneity of variance. So is what you do is you basically test your HOV. So this is called HOV. and it's your larger variance divided by the smaller variance. So if you look back, we had sums of squares. These are equal sample sizes. So truthfully, we could just use the sums of squares and not variances, but I'll use the variances to show you as an example. So our sample 2 had the larger sums of square, which means it would have a larger variance. So 86.8. So we'd have 86.8 divided by 4, because the sample size was 5, so we degree of freedom. And that would be divided by 52.8, right? 52.8 divided by 4. So, because sums of square, or variance, if you remember, variance is sums of squares divided by degrees of freedom. So if you take 86.8 divided by 4, I put that in parentheses, and then I hit divided by parentheses, 52.8 divided by 4, and put in parentheses, I got 1.64. 1.64. Now, this is a little different than how it's presented in your textbook, but that's okay. All I want you to do is calculate your HOV, and you can assume that you've met HOV if this value is less than 2. Because what it means is that the larger variance was not more than twice as big as the smaller variance. We don't want it to be more than twice as big. So in this case, we met homogeneity of variance. So we can assure whatever results we come up with are valid. If we don't make or meet homogeneity of variance, then it's more than likely our results are problematic. So now that we have our sums of squares, we can plug our sums of square values into the pooled variance equation. If you remember, the pooled variance was sums of squares for group 1 plus sums of squares for group 2 divided by degrees of freedom for group 1 plus degrees of freedom for group 2. So we have our pooled variance is 17.45. We're one step away from that last calculation, truthfully. So now we have our pooled variance, we can plug that in to our estimated standard error. I'm sorry, I don't know why this blacked it out. What was it? 17.45. So as our estimated standard error equation is the pooled variance divided by the sample size plus pooled variance divided by the second sample size, all under the square root, okay? So if you look, 17.45, it was equal sample sizes, so it ends up being 17.45 divided by 5, because there's 5 in this group 1, plus 17.45 divided by 5, all under the square root. Now, again, like I said, when I plug that in, make sure these are two separate fractions, okay? These are two separate fractions. They're not 17.45 plus 17.45 divided by 5 plus 5 is not the same thing. So it's 17.45 divided by 5, and I hit equal, and then I do times 2. And then that answer, I take the square root of. And I get 2.64. So that's my estimated standard error. And I can plug that in to my actual test statistic. That was easy, right? I'm sure. Lots of steps, but this is I'm not gonna lie, the math is not difficult. Is what seems to be the most difficult for students is knowing their notations and staying organized with the math related to the notations. That is usually the biggest bugaboo, is those things. So our obtained test statistic is -0.985. So we're not done yet with step 3 of hypothesis testing yet. So we still have more to do. We have to calculate an effect size. So your textbook talks about 3 different effect sizes. There's either Cohen's d, eta squared, or omega squared. I'm only going to teach you how to calculate Cohen's d and eta squared. You don't need to learn a 3rd one. And truthfully, you can just learn one. You can learn just how to calculate Cohen's d. It's the most commonly used. And then, but make sure that you know what eta squared and omega squared measure. You should know those definitionally or like application-wise. So Cohen's d is the most common, and so it's computed to basically determine how much does the independent variable affect the dependent variable. So we'll look at these 3 different tests. So, ooh, good grief. So my little things are not showing up very well. So I'm going to show you right here our pooled standard deviation. If you recall, our pooled standard deviation is SP squared, right? Is that notation, right? And the equation is SS1 plus SS2 over degrees of freedom 1 plus degrees of freedom 2. Okay, so if you recall, our pooled variance, so a pooled standard deviation is this. Because if you remember standard deviation, to get standard deviation, we would take the square root of variance, right? So for this, we're basically doing the pooled standard deviation, but in the actual equation, so we have d equals mean 1 minus mean 2 over SP squared there, right? This here is actually a pooled standard deviation because we're taking the square root of the pooled variance. So we're plugging that 17.45 in there, taking the square root. Some of the biggest errors that I see students making is forgetting to take the square root. Because the pooled variance, if you take the square root of that, it's the same thing as a pooled standard deviation. And if you remember in the original, like for a Cohen's d, for one sample test, it was m minus mu over standard deviation. Well, this is basically the same thing. D equals m1 minus m2 over s pooled, and I'm going to put pooled for the standard deviation. But for some reason, they don't put that. They don't use this, and that looks like I said spooled. But instead, they put square root of the pooled variance. So it's just knowing that it's basically the pooled standard deviation. So once we, well, to go back really quick, if you remember Cohen's d, it measures the absolute magnitude of the treatment effect. It basically tells us the number of standard deviations that the independent variable shifted the dependent variable by. So the number of standard deviations that the dependent variable moved due to the dependent variable. In this case, 0.62 standard deviations. So the other ones that could be calculated are eta squared. It's also known as r squared, but it's known as eta squared. And this calculates the percentage of variance accounted for by the treatment effect. So it's not talking about the number of standard deviations that the dependent variable shifted due to the dependent variable. It's telling us the percentage of variance in the dependent variable that can be accounted for by the independent variable. And is what we use is we use, and this says r squared in your book. I think it has n squared, eta squared, you could use either one, but they're the same thing. So r squared or eta squared, they mean the same thing. Okay, and so what we do is we take our obtained test statistic and we square it. And then we divide by the obtained test statistic squared again, plus the degrees of freedom. So we end up looking like this. Remember, a negative squared is a positive. So if you're starting to get like weird negative numbers, that means that your calculator is holding that negative. So many of your calculators, you have to enter it in a special way for the negatives to cancel each other out. So I always say, if you're squaring a negative number, just drop that negative because it shouldn't be coming out as a negative. Make sure that you're accounting for that. So in this case, our eta squared is 0.11, meaning that 11% of the variance in the dependent variable in the depression can be accounted for by the treatment condition, 11% of it. Now, I didn't teach you the omega squared. Basically, omega squared it's the same meaning, but you don't have to learn how to use it. So it's still the percentage of variance accounted for by the treatment effect. Now, confidence interval has to be calculated. So we have all of our information from before, our sample means, our estimated standard error, so that's in the denominator, and our degrees of freedom that we used for the total study. Now, if you remember, our original hypothesis said that the depression was going to decrease. So the original critical value we looked up was 1 For our confidence interval, remember it's a range of scores that we would see in the population if the null was true. A range means there's a lower number and an upper number, meaning that we should be looking at both ends, 2 tails. So that means we actually have to go back and look up a new critical value for 2 tails. So if we look up degrees of freedom of 8, and we look in the 2 tail column, our critical value for the confidence interval is 2.306. So that correlates with a 95% confidence interval. So then we're going to solve for our equation. So this is basically what we're estimating our means. So I usually take the mean 1 minus mean 2. I take that difference, and then I add and subtract to the product of the t critical value times the estimated standard error. So I usually take this total, the product, and I subtract it from the difference between this, and then I add it to the difference between that so that I can get the lower boundary and the upper boundary, which is negative 8.69 for the lower boundary. The upper boundary is 3.49. Now, before with the one sample t-test, we'd said, oh, if the population mean falls in between there, then we're retaining the null, because that's what we're testing against, that null. And the null in the one sample t-test was the population mean. But the null in independent t-test would be that there is no difference. There's nothing, there's no difference between, no significant difference between the sample mean, the 2 sample means, which would be reflective of the 2 population means. So that means if 0 falls in between those, the range, the lower and the upper, then we would be retaining the null. So as you could see, now we're ready to state our APA results. I use Cohen's d. My standard is using Cohen's d. You have the option on the exam to use either one, but I always recommend using Cohen's d because I've actually seen students get Cohen's d right, but not get the t obtained right for some reason in some mix-up calculation. But with eta squared, you're using your t statistic to calculate that. So if you've calculated that wrong, that means you've got your t statistic wrong and your effect size wrong. So this increases your probability of getting more points on the exam if you use Cohen's d. So if you like that little scenario. So here's our results. It wasn't significant. So the new therapy did not significantly decrease depression more than the traditional cognitive therapy. As T of 8, that's our degrees of freedom, equals negative 0.985. P is greater than 0.05. We know that it's greater because, remember, we had it to where here's where it would be significant, right? Our test statistic fell over here though, okay? That negative 0.985, meaning if you look, here's where our mouth is, okay? Our alpha, it is over here, right? Here's our P value right at this line. So P is being eaten, right, by that crocodile or whatever it is, however you want to memorize that. Then we state it as 1-tel. D equals 0.62, that's our effect size, and you don't need to have the little hat over D, that's just an official way. And then 95% CI in brackets with the lower boundary, comma, upper boundary. This is required formatting. And on the exam, you will be required to format it in that manner. So make sure that you're formatting appropriately. So hopefully that helps you with those APA results. It is a format, and it's a standard format, just like a language. You don't want to mix up your verbs and nouns if you're speaking Italian, otherwise people won't understand you. Well, this is speaking statistics, and people won't understand you if you're mixing up the information. It's not coherent to researchers or people reading the research. So really quick, I was going to go over the independent t-test and how to read it in SPSS or PSPP, but unfortunately it's not coming up. So this is what I plan to do, and you will only know this if you are watching this video, but as you'll notice, there's some empty little sections here. I am going to post these in Canvas, and is what I will do is I will post a link to these 2 slides in this in the active engagement for independent t-tests. I will post them in one of the active engagements. And is what I want you to do is read over the tables. There should be 2 tables within the slide. And I want you to write APA results for this independent measures t-test using the output, okay? So once you write those results up, just shoot them to me and via email and let me know, oh, this is the extra credit for the independent T SPSS activity, and shoot it to me by email. Now that's going to be, I'm going to post it as a separate practice activity. It won't be an active engagement, but it'll be called Independent Measures T-Test PSPP activity. And you're going to open it and you're just going to see the tables. But unless you've heard this, you're just going to be like, I don't know what this is. And you're going to either, number 1, have to ask me, or number 2, you're going to know and you're going to recognize it and you're going to go, oh yeah, she wants us to write the APA results using these tables. And to do that, also, you're going to need to open up, which is in your lab 3, it's how to read the PSPP tables for independent measures t-test. You're going to need that too. So if you can do all that legwork, you'll earn yourself some extra credit. Hopefully this was helpful. Please come see me in my Cranium office hours if you have questions or you need help.